So today I'm going to talk about smart pneumatic artificial muscle actuator with embedded microfluidic sensing. So I'm from Carnegie Mellon University, and this work was done at Harvard University when I was doing my postdoc. I just moved to Carnegie Mellon this September. So the background of this project is a soft wearable robots. We are interested in building soft robots which is wearable. So in that case, we don't have any rigid structures and also rigid materials. So some examples are my previous work. Such as this. So here we use pneumatic actuators to actuate the ankle motions. Here we don't have any rigid frame structures, but we use some bio-inspired tendon ligament systems and McKibben type pneumatic muscles to actuate sagittal motions and also medial lateral motions, like this. So another example is the continuation of this work, which is a little bit more generic version of the previous one. So here we made elastomer sleeve you can wear. So it has embedded sensors and embedded actuators. So it makes some whole body contraction effect and also bending effect when you actuate different muscles in different timing. So eventually we want to build something like this. Some materials with actuate arrays and also some sensor arrays. Then you can actuate different ways to actuate your joint motions. So then we focused on pneumatic artificial muscles, which is usually called the McKibben type muscles. Here we have mesh, nylon mesh, and also rubber chamber. So when you inflate this rubber chamber inside, because of the constrained geometry of this nylon mesh, it contracts in axial direction, but it inflates in radial direction. So this is the muscle I made in the lab. So we have capability of building this kind of muscle, different size, different diameter, and different length. And then we also developed another muscle inspired by these muscle fibers. I embedded Kevlar fibers in the elastomer tube. So there's no rubbing parts. So there's only one piece with embedded structure. So here you can see when you inflate, because of the constrained length of this Kevlar fiber, it makes axial contraction. So when I built this muscle first, I was really excited. I made some bio-inspired muscles, but then later I found this one. So exactly the same design more than 50 years ago. So then I started to think, what is the novelty and scientific contribution? So I looked at biological muscles first, and then I found a very interesting organ called the muscle spindle here. So this is located the belly of the muscle, but it detects the contraction length of the muscle itself. So when you think about the pneumatic muscles compared to electrical motor, because of the nonlinear behavior, it is really hard to control. So people add more external sensors, force sensors and position sensors, and which makes the system bulkier and more complicated. So I thought if we can integrate this kind of sensors in our pneumatic muscle can be more applicable and useful. So based on these biological sensors, I designed our embedded sensors in the pneumatic muscle. So we have this gray soft sense technologies using liquid metal. So it has elastomer layer with liquid metal embedded microchannels. So when you compress the top surface, it increases resistance because you are decreasing the cross section of the microchannel. And then also when you stretch, it increases the resistance again. So by having this kind of multi-layer sensors, we can we can fabricate a multi-axis strain sensing and also pressure sensing material, which is flexible and also stretchable highly. So my idea was integrating this kind of sensors in the pneumatic muscle. So I started the design, and then this is my design. And so we have elastomer tube with embedded Kevlar fibers. Kevlar fibers are flexible but not stretchable. So when you inflate, because it constrains the motions and it makes axial contraction. But because it's inflating in radial direction, here is embedded microchannel in helical way. So this microchannel will expand with this elastomer tube. So this microchannel will give increased electrical resistance. So we can have embedded sensors in the pneumatic actuators like this. Now we have to build this kind of complicated structures, and then this is our novel fabrication process. First, we have outer mold and inner mold. Inner mold makes the air chamber, and then these black things are Kevlar fibers. Now you align these Kevlar fibers in straight way, and then you pour liquid polymer inside. And then when you remove the outer mold, which is blue, you have these structures, cured elastomer with embedded Kevlar fibers. Now you wrap this cured structure with very thin, low friction fibers in helical way. And then we pour again outside of this structure. And now when you pull this low friction fiber, it leaves helical microchannels inside. So now we have three-dimensional helical microchannels inside. So this video shows the removal process of these thin microfibers. So these yellow lines are Kevlar fibers, and so when I pull this black fiber, it leaves a trace inside. So I remove the half of the fiber, and now I remove the other half of the fiber. Now it has helical microchannels inside. Now if you zoom in, you can see microchannels made inside of this elastomer structure. So now we have to inject liquid metal inside of these microchannels. So the video shows the injection process. This is really quick. So it starts from here, and then it ends here. But this is really quick, so you have to be concentrated. So I'm going to play again. So I'm injecting this liquid metal in the microchannel, helical microchannel, using just a syringe, a very thin syringe. And now we have the prototype. We have a microchannel filled with liquid metal, again, eutectic gallium indium, which is the liquid metal maintaining the liquid state at room temperature. And then we have Kevlar fibers under this microchannel. And also we have air inlet. Now, so when you inflate this muscle, it contracts, and then this microchannel elongates, so it increases the resistance. So this is the characterization result. So now we have 0 psi, 9 psi, 15 psi. It makes more contraction, but it elongates more and more the microchannels. So for actuation, I apply the different air pressures from 7 psi to 15 psi, and then I measure the contraction length and also force. So with a very low pressure, it shows here, but if you apply 15 psi, the initial contraction force is about 65 Newton. And then when you increase the contraction more and more, that force decreases. This is really typical behavior of the pneumatic actuator. And now we have to see how well it works as a sensor. So I measured, during this process, I measured resistance change of this microchannel. And so when you increase the contraction from 0 to 10 millimeter, which is about 25% of its original length, then the resistance was increasing from 0 to, so this is the resistance change. So resistance change was from 0 to about like 5 ohm. And this was pretty linear. So we were really satisfied with this kind of prototype. So as a summary, the objective of our project was to build the pneumatic artificial muscles with embedded sensors. And then the enabling technology was a microchannel embedded in soft sensor structures, and also the three-dimensional microchannel fabrication process was the enabling technology. And as a result, we were able to detect the position, which is contraction length, and also the response of the sensor was pretty linear. So as a future work, so we want to add more sensor capability. So now we have a position sensing capability, but we also want to add more sensors so it can detect the force sensor. So, and then we want to reinforce the elastomer structure. So currently, the elastomer structure is not really strong and sometimes not very robust. So by designing different ways, we want to increase the robustness. And also, we need to develop analytical models of these elastomer muscles. And then we want to implement these actuators, smart actuators in soft wearable robots like this. So when you wear the device like this, sometimes it increases the stiffness of your joint, and sometimes it helps your bending of your joints. So, so this is my last slide, and then although this work was done at Harvard, so Affiliation currently is Carnegie Mellon University and Harvard University, and then this was funded by NSF CNS program, Cyber Physical Systems program, and also this Institute for Biologically Inspired Engineering. So thank you very much, and I'd like to get any questions.